Hello. Okay. Any question from this time? Once again, we will have our midterm next week. 这放在桌上了。Yeah. So if there is no question, let's keep teaching something. So yeah, last time we go over this convergence of Fourier series. We see that there are three dilation conditions. So first one, if the signal is absolutely integrable. Second one, you don't have too many maxima and minima. And the third one, you don't have too many discontinuity. Then your Fourier series will converge to a signal, pointwise in this sense that for t, there exists on n such that your x sub n will go to your x of t. But we see that there is something funny. So if you have discontinuity, then you can have this Gibbs phenomena where you have this finite overshoot that never goes away, but it will get closer to your discontinuity. Okay. And anyway, the moral of the story here is that we have some kind of convergence for everything we study in this course. And yeah, and also the convergence we want is the energy of the air. It goes to 0 as n goes to infinity. And the lateral condition is a little stronger. We have this x sub n of t go to x of t at every t. And if there is no question, then let's go back to the properties of continuous time Fourier transform. So we go over this once last time. Let's go over this again more carefully. So the idea is that we can transform back and forth between our periodic function x of t and those Fourier series coefficient ak. And the back and forth are here. So first equation is the synthesis equation. This is how you get x of t from ak. And then there is analysis equation where this is how you get ak. You multiply x of t with some complex exponential and take the complex exponential with k, then you integrate them, then average them with 1 over t. Yeah. And so we can go back and forth between x of t and ak, and I want to see what happens if we change x of t to some x of t that's related to x of t, and maybe there will be corresponding change in the ak. So we don't need to go through this whole summation or the integral every time. Yeah. And the first one is linearity. It says that if you have some x of t whose series coefficient is ik, and there is another y of t whose series coefficient is bk, then you take a linear combination of x of t and y of t and call that z of t. That's a times x plus b times y. Then the corresponding Fourier series coefficient of z will have the same linear combination here. So it will be a times ax plus b times b. Sorry, a times ak plus b times bk. And you can check this. So this is actually two relationships, but they are both very easy. Just plug in the relation. Okay. Say if you want to go, let's say, from this side to this side, then you sub this x of t to ax plus by, and you will see that the integration is linear, so that ax plus by give you aa plus bb. And similarly, if you want to go this direction to this direction, then you plug in here, so you see that a times small a plus b times small b here. And once again, this summation is linear, so that will give you x plus y. Ax plus y. Okay? That should be easy. And the next one, the trivial one, is time shifting. So we say if x of t has Fourier series coefficient ak, then we do a time shift on x of t, and we go to x of t minus t naught. And let's say it has some Fourier series coefficient bk, and then we can calculate what's bk here. So we plug in our, let's see, we use our analysis relationship. So so we do calculate the bk brute-forcely. So bk should equal to integration of x of t minus t naught e to the minus jk omega naught t dt. So this is just plugging the formula, this formula here, with x over t become x over t minus t naught. And then we do a change of variable. Now we just look at this formula and try to put it into a form that looks like ak. So we say tau equal to t minus t naught. And so we are switching every t into tau. So there is this t here, t minus t naught, that should become tau. And there's another t here, so this is t. So tau equal to t minus t naught, so t equal to tau plus t naught. So it becomes tau plus t naught. Then dt should equal to d tau, because t naught is a constant. Okay. So it becomes this thing. And we see that this extra t naught term, it doesn't depend on tau, so it can be kicked out of the integration. So we get extra e to the minus jk omega naught t naught here. Okay, this is just from this t naught here, and everything else now we have the integration of tau here. But you realize this tau is the dominant variable, so you can rename tau back into t. Then this whole thing is just ak. Okay, remember ak is this thing. Okay. So yeah, it's 1 over t integration x over t e to the minus jk omega naught t dt. Okay, so this is just ak, and so we see that the bk is ak with this extra factor of t naught we get. So if you get a time shift on your signal, then you get a phase shift on your Fourier series coefficients e to the minus jk omega naught t naught. Okay, question. Okay. And then we have time reversal. So the derivation is different. So I guess both ways we can use. So this time we use a synthesis equation because this is simpler. So we think what is x over minus t. So because we have x over t equal to all these things, then x over minus t, so you just change t to minus t. Okay. And you have minus t here, then you get a minus sign here. And what you do next is, once again, you do a change of variable. So you change m to minus m. So if you want to be very careful, you should say like minus m prime equal to m, and you change m prime to m. But we are skipping a few steps, like one step here. So anyway, you change m to minus m. So this m become minus m, and this minus m here become m. So we get back to our jn 2 pi t. I guess I should just say k here. So we have minus m equal to k. But anyway, so you get a minus m here, and you get plus m here. So now this is back to the form of Fourier series. Because we have the jn 2 pi t over big T, which is equal to, which is, if you use m as k, so this is e to the jk omega naught t. And okay, and there is another change. So the summation, so we have m from minus infinity to plus infinity. But if we change m to minus m, that's still minus infinity to plus infinity. Okay. And anyway, we arrive here. So we see that once again, this is in the form of Fourier series coefficient, Fourier series. Sorry, so the Fourier series synthesis equation, and you can just read that. So the corresponding bk should be just this a to the minus m. So if it is, okay, maybe I mark this, then we can change later. Okay. Be easier. Okay. So yeah. So anyway, right? So bk equal to a of minus k, and we see that so we see the Fourier coefficient of a to the minus t. We just write it a of minus k. Okay. Let me mark this. So we should just have k here. Doesn't matter because it's dummy variable, but it's better form. So ak, ak, and ak here. Okay. Yeah. And then we have time scaling. So this is a funny thing. So time scaling don't actually change the Fourier series coefficient. Because when we do time scaling, so here we assume A is positive real. Let's say A is bigger than 1, then we will do, say we have some periodic function, periodic like this. And then we do time scaling, then as we say in chapter 1, so say that A is bigger than 1, we'll squeeze the signal. So the height should stay the same. Let me draw this better. How do I eraser? Okay, that's just okay. Wait, what? Okay, Control P. So if we do time scaling, then you will squeeze the signal. So maybe you look at this again. So you see that this will actually change the period, right? Because the period before is this t, and we will get a smaller period t here. And this is t over a. And yeah. So when you do time scaling, you actually change the fundamental period, and you also change the fundamental frequency. It becomes a omega naught. And but actually the series Fourier coefficient will not change, because you can look at this formula. So you see that you can get another synthesis equation without changing the AK. You just change t to at, then you can solve this a to u omega naught. Then this equation is still satisfied. So all the series coefficients, those a sub k, don't actually change, but you will get a different different signal by having a different fundamental frequency. Okay. Question? No. Okay. And then there is multiplication, and as we said, we have once again two signals, x of t with coefficient a sub k, and y of t with coefficient b sub k. And we can calculate the series coefficient of xt, yt by doing, well, we use both equations. So we say, so we use the synthesis equation for x and y. So x times y should equal to this blue part, right? Because x is summation is an, and y is summation is bl, and the exponential we already combine here, e to the j n plus a omega naught t. And so this part is x of t times y of t, and then we use the analysis equation back to get to the ck. So we take x of t times y of t, and then we do this multiply e to the minus jk omega naught t, the integration. And also you see we don't use k here because we already have k here. So we want the dummy variable have different names. So this is NaL here. And anyway, we have this thing. And to solve this, we will do the usual trick. So we will switch the ordering of integration and summation. So we solve this integration first. And so this integration will be on t, right? So we need to look at the part with t. So here we have a t, this exponential from x of t, y of t, and here we have another t. And but anyway, that's in the term of e to the j n plus l minus k omega naught t. And this is the orthogonal thing we talked before. So we had that this integration of, so it's just a reminder, this integration t, 1 over t, e to the jk omega naught t, and this is equal to 0 if k not equal to 0, and this is 1 if k equal to 1. K equal to 1. And if you want to say this thing, and if you want to write this in function, then you see that, oh sorry, I got this in wrong order. So this is 0, wait, 0 if it's not equal to 0, this is correct, and it's 1 if it's equal to 0. So this is just the discrete time delta function, right? No, we are assuming all those k are integers. Yeah, and so that's just the discrete time delta function. So we write it as a delta function here, delta of n k. So it's the n plus l minus k, but the delta function is obviously even, so that's also k minus n plus l. And okay, so the integration becomes the delta function, and then we solve 1 over the summation. So we sum over n, then you see that this thing, if you want to be not 0, n must equal to k minus l. So n becomes k minus l, and this summation disappears, because this summation cancel with the delta function. So you got, so n become, oh sorry, I got the order a little reversed, but so it should become okay, it should become a of a sub k minus l and b sub l, but then we see that that's a convolution formula, and or we can do another change of variable, and that's summation a of b sub k minus l. Okay. So ordering is a little funny here, but anyway, any question here? So this is a little funny, so let me mark it down. But yeah, but that's the idea. You do the integration first, you get a delta function, and here we can sub all l with k minus n, and we change the name to, and we will get this thing. And anyway, you see the ck, or we actually use hk here. So let me also mark this. I should change this back to c. This is annoying. So ck. So ck is this summation, or we can also change this back to k. Oh no, change this back to n. Anyway, ck is the summation l, a sub l, b of l minus k minus l, and we see that if we think those l and b k minus l are the discrete time functions of some a of l, and then this c of k is just the discrete time convolution between ak and bk, and as we said last time, this is a very general thing. So if you take the multiplication of two functions and you do a Fourier transform, you will get the convolution of two coefficients. And actually the reverse direction is true. So you see that we take the multiplication of two coefficients, then it will corresponding to the Fourier transform of the convolution of two functions. So you get convolution on one side, you get multiplication on the other side. And this one I don't do a proof, but it will be very similar to this, and it will be one of the problems. So any question here? Not? Okay. Then we see next one. So conjugation. We have x of t with ak, then what's the coefficient of a start? And this one, I believe you can just, well, we do this when we talk about real signals, and Then we just look at the synthesis equation and we see we do convolution. We take the conjugation on this side, and we do conjugation here. Then we will see AK become AK star, and you get HR minus sign here. You get the HR minus sign by conjugating this e to the JK omega naught t, and then you absorb the HR minus sign with your K, so your AK also become A minus K. So if you get X to X star, then you get some BK equal to A star minus K. And onto the most of the time we use this is when X over T is real. Then we'll have AK equal to A star minus K. Or you can switch things around a little bit, that means AO minus K will equal to A star of K. And also from here, you see that you will need to have A0 to real, because 0 equals to minus 0. And also absolute value of AK should equal to absolute value of A minus K. This is just something the coefficients for this coefficients of real signal should satisfy. And we have checked these things before for the cosine function. Okay. And finally, possible relation. It means that the energy of the signal equal to, if you also look at the coefficients of the signal, then the energy of the coefficients will equal to the origin energy of the signal. But the normalization, you just need to remember. So the normalization that works with our notation is that the average energy over one period for the signal equal to the total energy. So this K is from minus infinity to plus infinity. So the total energy of every coefficient. And the proof is once again in a homework question. So you just need to check it out. Yeah. And finally, we have the differentiation and the integration. Now this one is more tricky. I believe this is not actually in textbook, but it's in the cheat sheet here, so let's talk about this. And this one is tricky. Okay, so the differentiation is actually okay. You can derive this differentiation very easily by just taking the synthesis equation. So you take a differentiation on both sides, and this side becomes dx dt. And this side, the only seating boundary is this e to the jk omega naught t. And so you do differentiation on the exponential, you just get the HR factor of the coefficient here. So you get the HR e to the, you get the HR jk omega naught here, right? When you do the differentiation. And yeah, so this side becomes summation k, and with the HR e to the jk omega naught t multiplying your ak. So you just get your new coefficient is jk omega naught ak. Okay? So that's very cool. It's a nice equation you can use. And what's bad is, so now we have the integration formula here. Wait, do we not? Yeah, we have the integration formula here. And sorry. And now this formula is actually troublesome. So the idea here is you want to take the reverse direction of this thing. So the reverse of differentiation is integration. Okay, that's okay. And then when you do differentiation, you get HR jk omega naught. And so you get integration, we get 1 over jk omega naught. Now I think this is funny because this k can be 0, so 1 over jk omega naught can give you infinity. So how does that make sense? And the short answer is that then you need to have AK needs to be 0 for this to have any sense, because A0 must be 0. So when k equals 0, you get 0 over 0. That can be something, and that makes some sense because you think about you're integrating over your x of t, and A0 is the constant term. So if you have yeah, so A0 is a constant term. So if you have non-zero constant term, and you're integrating over this infinite area, infinite length, then your thing will blow up. But I think so. This is not in the book, but I think this formula is just unusable most of the time because you want your signal to be this integration from minus infinity to t over x over t. But remember, your x over t is periodic, right? And yeah. So your x over t is periodic because here we are talking about periodic signals. So x of t is like something that keep doing the same thing, right? So some periodic function that keep repeating itself. And then it's a periodic function, so this x or minus infinity will not converge to anything because it's going to oscillating up and down. Unless x is actually a constant function, trivial case. But okay, so x over t is on the x over minus infinity is undefined, so I don't think you will ever have a function that's well defined that equal to this minus infinity to t x over t. So you can actually never use this because your function will never satisfy this form exactly. So it's funny, but we'll see soon in an example that we will still kind of use this thing by using a reverse of dx dt. So this differentiation relation is very well defined, and yeah, you can find the differentiation of a periodic function. You will still be a periodic function, and so if you think about you want to apply this in reverse, then actually then your AK needs to be then your OA0 should be 0. And the new A0 you need to be calculated. Actually, I think differentiation. But anyway, we'll see that in an example. So you will see that when you try to reverse this differentiation, then you need to calculate your new A0 separately when you try to apply this. Okay. And let's see. So your function. Okay. Okay. So if we try to reverse, then this probably don't need. Let me think about this. So we probably don't need this. Differentiation. Oh no, it should still be 0. Okay, yeah. So okay, it's a little more complicated, but anyway, so OA0 should be 0, and because if you are differentiation of something and you are differentiation of a periodic signal, and so yeah, that should be 0. And anyway, so the new A0 will need to be calculated. We'll see this in an example. And anyway, here is the table, which is a bit small. Let's see, can we do this? Okay, yeah. So here are all the things we talk about, and I believe there is no more. Yeah, we talk about all of them. Real. Oh, we didn't talk about even and odd. We'll probably talk about this later. Yeah. We didn't talk about even and odd, but it's very similar to the real thing. Anyway, that's the table. And if there is no question, let's see an example of how to use the table to calculate our coefficients a little easier. So yeah, we have G of t here. Look at this. Quite blocky. It has this constant between -1/2 and +1/2, and it's very discontinuous, so it keeps up and down, up and down. So we want to calculate the Fourier series coefficient for this periodic G of t. And obviously we can use our analysis relation to just do the integral. But we want to avoid doing an integral by using the properties. So the properties is that we try to shift this x of t around to fit it into this g of t, because we already do the integration on this x of t, this square wave. So before we have this example 3.5 where we do brute force integration over the square wave, and we have seen its Fourier series coefficient. And we see that g of t is very similar to x of t. So x of t is this thing that's periodic with big T and has this square with width minus t1 to t1. So if we set big T equal to 4 and t1 equal to 1, and so this will be minus 1, 1, and 2, minus 2, 2. And then we shift this to the right a little bit and pull down it by 1/2. Then you see this will be the same thing, right? So we shift to the right by 1 unit. Then from minus 1 to 1 it becomes 0 to 2. And then we pull down by 1/2. So this 1 to 0 become 1/2 to minus 1/2. Right? So we can shift our square wave signal around to this also square wave signal. That's a little more symmetric. And g of t will equal to x of t minus 1 minus 1/2. Okay? This is the operation that we have in chapter 1. Okay. And then let's see how the coefficients shift around. So first we write down all the coefficient for x of t by the solution we had before. So from example 3.5, before we have like a general t1 and t. Now we plug in our t1 equal to 1, t equal to 4. So a0 we say is 2t1 over 1, so it becomes 1 over 2. And ak is sine k omega naught t1 over k pi. Then we see that omega naught t1 equal to 2 pi over t times t1. And then once again use is 4 and 1, so that's pi over 2. So your ak is sine k, pi k over 2 over k pi. And now we shift this one by one. So we have the coefficients for x of t, then we want to have the coefficient for x of t minus 1. And so this is the example of the time shift relation. So let's try to look up it here. So we have a time shift here, x of t minus t naught. You get, okay, so it's really small. You get this ak with a traffic e to the minus jk omega naught t naught. Okay? And so we get e to the minus jk omega naught t naught. So t naught is 1, and omega naught is 2 pi over t, and t is 4, so that's 2 pi, so that's pi over 2. So we get this a factor of e to the minus jk pi over 2, and times 0 ak. And so that's a Fourier series coefficient. And then how do we get this h1 minus 1/2? We didn't talk about, so yeah, so that's not a formula, but we can think this as another signal. So we think this minus 1/2 as a constant signal. And the constant signal has very simple coefficient. It's a constant, so it's not oscillating at all. So for every k naught equal to 0, the ak equal to 0. Okay, we try to say ck. So the coefficient for k naught equal to 0 is ck equal to 0. And for k equal to 0, so the constant term is just this constant minus 1/2. And then we use the linearity, so this signal plus this signal. So the coefficient should be adding together. So the coefficient for x of t minus 1 plus, and then plus this minus 1/2 signal, you should add these two together and it become ak e to the jk pi over 2. For k not equals 0, and for k equals 0, you need to is h1 minus 1/2. And then finally you plug in the ak up here. So for k not equals 0, we have this thing. So, well, it's just writing it down. So this is sine k over k, and with your hr e to the minus jk. And for the 0 term, now this is a little more interesting. Okay. So for this extra term, we have 1/2 minus 1/2. So this is 0. And we see that check out because this thing, if you average over one period here, then you have this negative part and the positive part cancel out each other. So we think it should have the DC term being 0 because average over one period, your signal is 0. Okay, so that's some transitivity check that we are doing our calculation correct. Okay, any question? Okay. So we see that we can save some integration. So now we see that we have done the Fourier series coefficient for this square wave signal. Then we can move this around and stretch, then etc. Stretch, then stretch, squish, then and move this up and down, left and right. And you can all use those similar coefficients and derive the coefficient for the new function. Okay, question? If not, then let's see a more interesting example. Okay, so now we have another function, we call it x bar of t. X bar of t is this thing. It's very related to g of t. So x bar of t has a straight line from 1 to 0 between minus 2 to 0, and have this straight line from 0 to plus 1, from 0 to plus 2. And so it's related to g of t because it's a derivative of g of t, okay? And we can just, sorry, its derivative is g of t. And okay, so we can just check when we have derivative on this line, so the slope is minus 1/2, right? Because it takes tan 2 to go from to get minus 1. So derivative of this part is minus 1/2, so let's check out. And the derivative of this part is plus 1/2, let's check out. And it's in the same periodic between minus 2 and 2. Okay, so we have dx bar dt equal to g of t. Okay. So let's write it here. So remember dx bar dt equal to g of t. Okay. Now we use our differentiation relation to relate the coefficient between x bar of t and the coefficient of g of t. And you can see here that so the another thing we had before should check out. So g of t has the a0 equal to 0. And that makes sense because when you integrate the g of t over one period, that should become integration of a0, and that should be the difference between x bar of t over one period. And because the x bar of t is periodic, so like the value of this point minus the value of this point should be 0. Right? So if your g of t so if your x bar of t is periodic, then this derivative g of t should have a not equal to 0. Okay. And anyway, let's solve the rest of the problem and find out the coefficient for x bar of t. So as we said, we can, so the coefficient of g of t, we call it dk. It should relate to the coefficient of x bar of t called dk, so it should relate it by the formula we had before. That is, dk should get hr jk omega naught. Yeah, let's go back to see we having the right equation. Yeah, so we have the h bar jk omega naught, and we have its place, and sorry, and well, our omega naught is pi over 2. Okay. So dk is jk omega naught times your ek, and so this has no trouble when k is not equal to 0, so you just move k to the other side. And so your ek is your dk divided by jk omega naught, so it's 2 dk, and you have jk pi, and then you just look back to your dk, so your dk is this thing, and then now you get even more terms here, and so you do the multiply by 2 divided by jk pi, and you get this thing. So this is ek, 2 sine pi k over 2 over j squared parentheses k pi squared, and times e to the minus jk pi over 2. So this is k not equals 0. And so for E0, then that's something we need to be more careful. So for E0, so D0 equals 0 as we said, but k also equals 0, so that's 0 over 0. That's undefined. And that's undefined because this G doesn't know your DC term, right? So you can think about you shift this x bar of t, you shift it up and down, then you will have the same derivative. Because when you do derivative, then the constant goes away. That means that, say, if your x over t actually equal to something like this, so if you actually like from 2 to 1, right, instead of 1 to 0, so your x bar of t actually, so you have x bar of t. T look at this, then everything we said before will still work out. Okay? So obviously this g of t doesn't know the DC term of your x bar of t. So if you want this e naught of your x bar of t, you will need to look at your function directly. And yeah, so you just do the analysis equation. You just do the analysis equation on your x bar of t. So you average it over one period to find out your e naught. And well, you average over one period here, then you get 1 over 2. So e naught is 1 over 2. Okay. So that's examples of how we use Fourier properties of continuous time Fourier series to get coefficients without doing too much integration. So, any question with the example? We see that with this differentiation property is more tricky in that you need to deal with the constant term more carefully. Okay? Yeah. So you have this x bar of t. Let's finish this. We have this x bar of t, then x bar. Maybe I shouldn't say x bar. Let's see. X bar is a funny notation. Oh. So let's say we have some. What's the good name? X prime of t from 2 to 1, right? Then we also have dx prime of t dt equal to g of t, but we will have integration over t x prime of t dt equal to 3 over 2, and this is like e prime of 0. Okay. So you see this new a0 thing depends on what this integrated function actually look like. Okay. If there is no question, then we are finished with the properties. And so we have 5 minutes. Let's see. How about we have a break earlier and start the next class earlier? Okay, because we are going to talk about different things. So let's start the next class on 4:25. We have a 10 minutes break, and let's start at 4:25, and maybe we'll finish class earlier today. Okay. Hello. Okay. Yeah. Let's start. So those are the properties of the continuous time Fourier series, and so we are so we are finishing our continuous time Fourier series. So let's go to the Fourier series representation for discrete time periodic signals. And so this is very similar to continuous time Fourier series, except that it's even a bit easier because there is no convergence issue, as we are going to see very soon. Okay, so yeah, we want to write periodic functions as harmonic complex exponentials, but let's repeat the motivation for writing things in complex exponential once again. because this is because we care about LTI system, and we have said in the very beginning of this chapter that z to the n are eigenfunctions for discrete time LTI system. If you put those into this as the input to your LTI system, you will get an output that's proportional to your z of n, and the eigenvalue will be a function of z. So how the eigenvalue depend on your z is the characteristic function of your LTI system. But anyway, a lot of this chapter we don't actually talk about system. We care about how to decompose our signals into those complex exponentials. So yeah, complex exponential is what we like here, and to write complex exponential as z of n, we just say we can pick z as e to the jk omega naught. Then we'll have those functions e to the n is equal to e to the jk omega naught n. Okay, so those are the discrete time complex exponentials. And if you pick your omega naught correctly, then it will be the harmonic complex exponentials. And anyway, we consider our periodic function x of n. So if x of n is periodic, then xn should equal to x of n plus big N. But now this big N must be an integer. That's something special for the discrete time functions. Okay? And anyway, the fundamental period will be the smallest n, smallest big N, such that this equation is true. And the fundamental frequency we have here, the omega naught, will be 2 pi over the fundamental period as before. So 2 pi over big N. And we want to express x as a sum of harmonic related complex exponential. And harmonic related complex exponentials will just be those e to the jk omega naught n. So those zn we had before, e to the jk omega naught n. But now the omega naught is not arbitrary. So when we write here, we didn't say what's omega naught. But here we are thinking the omega naught should be the frequency related to the fundamental period of the function we want to express. Because remember, as we said before, in chapter 1, so all the harmonically related complex exponential, they will have the period, will have big N as their period. It may be not their fundamental period, but big N will all be their period, just like in the continuous time case. So we want to express x of n as the linear combination of all those harmonically related complex exponential, because we know all those e to the jk omega naught n, they are the eigenfunctions of every LTI system. So you write it this way, then you can write out the response of your LTI system very easily. Okay. And yeah, and we are going to see very soon that every periodic discrete time function can be written this way. And but let's remember something about the discrete time harmonic series first. So there is something different between discrete time and continuous time, in that the discrete time harmonic series, there are only big N terms. Okay? So in continuous time, the summation k is from -infinity to +infinity. But now we are writing this in ambiguous way, just say sum k. But actually, we are only summing k for kn terms. Okay? Because if you increase k from some k to k plus n, so like here, you increase k from k to k plus n, you actually get back the same complex exponential, because this thing is okay. So k to k plus n is equal to the same thing, because it's plus n thing. You just get h r j, and n cancel with n, you just get j 2 pi times n. But e to the j 2 pi equal to 1, and 1 to the nth power is still 1. Okay. So that's because a lot of the remainder, that's because we are our discrete signal, we only take in point at the integer point. Remember that we said that if you try to get a discrete signal, say sampling from a continuous signal, and because you are only taking point at the integer value, those 1, 2, 3, and so if your signal has a very high frequency oscillation, and then you only sample at the integer point, you don't see all those very high frequency oscillation. Okay, so the highest frequency you can see. So the actually highest frequency is actually when is k omega naught is around pi, like plus minus pi, or pi plus 2 pi n. Okay. And anyway, so there are any n big N harmonic series because higher frequency you cannot see, and you will just get back to the same convex exponential. And that means that this summation, you no longer need to take k from minus infinity to plus infinity. You don't need to take n consecutive of them. Or sometimes you can even take non-consecutive, but this is easier. And so for example, you just sum k from 0 to n minus 1. Or you can have 3 to n plus 2. Or maybe something around, well, it's discrete, so it's a little weird if you want to get a symmetry. So if it's even, then maybe you want a minus n over 2 to plus n over 2 minus 1. Yeah. Actually, is that n over 2? Yeah. But anyway, you want n consecutive integers as your summation here. And the other thing are similar to the discrete to the continuous case. So you have x of n equal to summation k in a n range, and ak e to the j k omega naught n. And once again, omega naught is equal to 2 pi over n. Okay. So this is the synthesis equation for discrete time periodic signal. Sorry, discrete time Fourier series. And Fourier series only work for periodic signal with period big N. Okay. Question for equation here. So we are just saying we want to express it as this thing, and then we are going to say why it's always possible to do this. Okay. And okay. So unlike continuous time, there is a bit funny way to calculate all the AK. This is by just solving linear sets of equations. So if we think about this thing, so x is a periodic function with period big N. So if we list out all its big N values, okay, so we can write all those values as so we can substitute this n with all the possible value and write down those synthesis equation. So x over 0 will be summation of all those ak, because then n equals 0, then this exponential is 1. And x over 1 will be summation of ak with different coefficient on every ak. So e to the jk, j2 pi k over n. And So we can write down all these equations. Okay? And now we can kind of switch the role of the equations. So now we see those sides. So this x0 to xn minus 1, those are just value, right? Because you plug in small n to your x of n, then you will get some number here. But this side will be like a linear combination of AK, right? So, for example, if I write this down, this out a little bit will be a little more clear. So this is, let's say we from 0, so this is A0 plus A1 plus plus A minus 1. And this will be also A0 and e to the j, and let's say just j, Let's write this back to omega naught because it's easier. J omega naught A1 plus e to the 2j omega naught A2 plus dot dot dot, etc. Right? So you can see this thing as like equations for your AK, right? And now those are just linear equations because all those AK are linear, and there are just finitely many AK because we say there are only n AK, and so there are n unknown AK, and there are n equations. So you can actually just get your AK by solving all the equations. And so here we skip a little bit. So you can very easily prove that the equations are linearly independent. So an equation, n linearly independent equation for n unknown. So you can solve every AK here. Okay. So you can invert so you can invert your synthesis equation to get your AK, and that's kind of your analysis relation. And this is a very different thing from the continuous time. Remember, continuous time case we have some weird counting, saying that continuous time we have infinite AK, and we also kind of have infinite value for x of t, right? So in a continuous time case, let's digress a little bit. For continuous time case, we have x of t, and we have also AK, and we say there are infinite AK, there are infinite x of t, but the infinite on x of t is kind of a little more, because if you think about in one period big T, then all those x of t value there are uncountably many possible t to pick your x of t. But for AK, there are only countable many k, because k is in integers. So there are kind of more x of t than AK. So you need some smooth condition on your x of t for this AK to actually make sense. But in the discrete case, the number of unknown xn and the number of unknown AK just match. There are big n possible x of n, you should fill in your value, and there are big n possible of AK, you should fill in your value. So there is no convergence issue. There is just an equation for n unknown, and you can always find those AK, and they will perfectly sum back to your x of n. Okay? Perfectly sum back to your x of n. So that's different. And anyway, but solving this linear equation is actually kind of dumb. So we still want to get our analysis relation with this orthogonal condition. Okay. So yeah, it's very similar to what we do in continuous time. You want to multiply your function with so basically you want to take your inner product of your function with the complex exponential, and in the continuous time we do multiply with this minus the exponential, the integration, but it's discrete time, so we don't do integration, we do summation. So what we do here is we multiply our function with this e to the minus jr 2 pi n, well, e minus jr omega naught n. Okay, and so we have the new variable r here. This should pick out your a sub r, as we're going to see very soon. But anyway, we assume we multiply our signal with this e to the jr omega naught n. And then we sum over one period. Okay. And so we sum over all the possible n basically. And then we get this thing. So we write x of n as our synthesis equation. So it should become summation k ak e to the j k omega naught n. Then those omega naught n thing combined become k minus r. Okay. And so these k-mans are seen when you sum over n, then you should get the orthogonal condition, and we have it already down here. So now we need to be a little careful about our summation. So we are summing over n here. Okay. So now the k over r, k minus r is something fixed, like some constant here. So anyway, so you have e to the j, k minus r, and omega n, and where omega n is 2 pi over n, then this thing will equal to big N if your k minus r is 0. This is obvious because if k minus r equals 0, then the upper side is always 0, then you are summing over 1. And there are big N terms, so the answer is big N. And it's 0 otherwise because we're going to see in more detail later, because if k minus r is not 0, then the and then you sum over all those bigger terms, then those will be equally spaced out points on a complex plane. So we are thinking these are the complex plane, and those are faces, right? So those terms are all non-1 values, non-1 complex numbers. So they are all on these non-1 complex circles. Okay, and if you think about these things, so e to a j k minus r, so if n equal to 1, then it will be some point, it will have some angle that's like 2 pi divided by n times j minus r, right? So we have some angle, and we have that angle times 2 times 3, etc. But that angle is a fraction of 2 pi, and so if you sum over all possible n's, then that will be equally spaced out point on your circle. And because it has symmetry, very symmetric on the placing on these circles, so if you sum over all of them, they average to the middle point of your circle, which is 0. Okay? And actually, question here, we'll have a little more algebraic derivation. But anyway, so this thing is true. So this is true, and now back to our Fourier series coefficient. So we have our x multiplied with this e to the minus j r omega n, and then we have a summation k, summation n, and we do what we always want to do. We change the order of the summation, and so NEC depends. So we have summation n first, and the thing that doesn't depend on n is ak and the summation k. And this thing we just spend quite a bit of time saying that is basically delta function thing. So this has value only when k equal to r. Okay. And okay, so this is the same equation. And yeah, as we said, this thing is okay. Anyway, so this is non-zero only when k equal to r, and so this is basically a delta function of k minus r times n, and then you have this sum over k over your delta function, then your k will become r. Okay. So this whole thing should become n times ar, because if k not equal to r, this is 0, so k can only be equal to r, and when k equal to r, this is n, and we get your ar out, this is the thing we want, then we move n to other side, then your ar equal to 1 over n, summation small n, xn e to the minus jr, 2 pi over big N, small n. So this is an analysis relation for discrete time Fourier series question, and yeah, and we probably want to switch r back to k. So ak equal to this thing with e to the minus jk here. Okay. And let's have a little summary on those orthogonality condition for complex exponential. Remember, we have this for continuous time and discrete time. they are kind of similar. So for continuous time, we have this complex exponential e to the jk minus n omega naught t. We're integrating over one period, and it will should equal to big T if your k minus n equal to 0. And so those kn are always integer, and those krs are integers. And it's 0 when k not equal to n, because this actually works for non-integer, but anyway, integer make more sense because for Fourier series those are integer. Yeah. Yeah. And as a reminder, when k not equal to n, this is 0 because you can brute force the integration. So integrating from 0 to t e to the is jk minus n omega naught t dt, then integration you take all, you have 1 over the coefficient here, and this thing, and your exponential here. Oh, okay, so you do need to have integer for this to be 0. And anyway, so this thing, because it's periodic with big T, so this e to the jk minus n omega naught t will equal to will actually equal to 2 pi multiple, and e to the j2 pi will equal to e to the 0 equal to 1. So the upper and the lower limit will be the same, and this thing is 0. Okay? And this only works because you need to have this 1 over k minus n. When k minus n equals to 0, then you have 0 over 0, and you actually plug in back, then you are integrating over a constant function, and so that's integrating over 1 of tan t, so that's t. And we have the 2 thing here, so we think about when k not equal to n, you are integrating an oscillating function, and the oscillating function you integrate back to 0. And when k equal to n, you are integrating a constant function over t, and you get big T. And similarly for discrete time, we are doing the summation exponential jk minus r. It's not n anymore because we have another small n here. So we have summation e to the jk minus r, and omega naught we write out as 2 pi over n, just because. So anyway, e to the j k minus r 2 pi over n times n summation over n is equal to big N if your k minus r is integer multiple of big N, and 0 otherwise. And so the 0 thing is, so this integer multiple is also easy. So it's an integer multiple of big N, and this big N will cancel with this big N here, and you have e to the j n times another maybe n. So anyway, you have a like e to the j n 2 pi, and that's just 1. So you are summing over n once, and you get n, and it's 0 otherwise, because so we have an algebraic derivation here. So you consider this summation when your k minus r is not integer multiple of n. Then you can multiply your whole equation with e to the j k minus r 2 pi over n. Okay? So basically just multiply the same thing here with n equal to 1. And okay? And you do this, and as we said, this is the same thing with n equal to 1, so you can put it inside, and you just get n plus 1. Right? The outside term just give you a plus 1 because it's basically a totally same thing. And but what does that mean? You can take n to n minus 1, and that doesn't change anything, because as we said, your n is just consecutive n numbers, consecutive big N number. So if you shift your summation from 0 to n minus 1 to like 2 plus 1, so you do 1 to n, then that's the same summation, because this whole thing is periodic. So you are back to your same thing, right? So this n plus 1 doesn't change anything. So this is the same expression. So the blue expression is same as this blue expression. And what does this mean? So blue thing multiplied with this extra phase equal to this blue thing, but so I write this wrong. Okay. What I want to say is actually okay. That's it is correct, but not quite what we want. So these two equal. Maybe let's write this. So ax equal to x, then a minus 1 times x equal to 0. Okay. So this should be 1. Okay. And anyway, so those two things equal only. There are only two possibilities as we have a very quick calculation here. So either the blue thing equals 0 or our phase equal to 1. Okay. But this is not equal to 1 because when equal to 1, then this k minus r should be like a integer multiple bigger n. Then that's only when you get e to the j 2 pi times n. Okay. But as we say that's not true, so this phase is not 1. Then the blue thing should be 0. Okay. So that's an algebraic derivation of why this is 0. Okay. And so I actually don't. There are too many dots in this equation, and we can put the algebraic equation in like a picture. So can I? Or maybe not. So let's say we have so the only parameter here is k minus r, k minus r over n. So if our k minus r over n equal to 1 over 3, so that's this trivial example. K minus n over 3 is 1 over 3. Then we are basically summing over where is this? Let's see, Control E. Okay, let's draw this better. Okay. We have a circle, and what we are summing over? We are summing over all those e to the jk over n, jk minus n times 2 pi and times big N, and so then times small n, and when small n equal, so let's write that down, e to the j, and so all those things equal 3, 1 over 3 times 2 pi times n. Okay. And so big N equals 0, then we have 0 here. Then we have 0 phase here. Sorry, small n equals 0, then we have 0 phase here. So it's this point. So we are writing this complex plane. So this is real and this is imaginary. And this point is 1. And then when n equal to 1, then we are at e to the 2 pi, e to the j 2 pi over 3. So the whole circle is 2 pi, and where 2 pi over 3 is here, this point, right? So this is n equal to 1, and when n equal to 2, we're here, and when n equal to 3, as we expected, we will back to here, but we are only summing over 3 small n. And we are saying that these 3 points, when I sum together, they should give you the middle point. Because if say their summation is some number, so some vector, say maybe this thing, right? This thing is, the code is big A. And if the summation is big A, then we can rotate everything by 2 pi over 3, because it's totally symmetric, right? So we rotate everything by 2 pi over 3. Then we are summing the same 3 points, because this point becomes this point, and this point becomes this point, and this point becomes this point. But your A will also get rotated by, okay, so now it's hard. So maybe here. Okay. So then this point is a times your e to the 2 pi over 3j. Okay. A becomes this thing, but it's the same summation. So A and your A rotated by 120 degree should be the same vector. And that can only happen when your A is 0 vector. Okay. So that's the idea here. And so that's when your k mass R over n is not integer. And when your k mass R over n is integer, then you are just summing a whole bunch of points that has the 0 phase. So if k mass R equal to m times n, then every point is on this 1 point, and they are summing over a whole bunch of 1, then you get big N. Okay. So this is the orthogonality of complex exponential, and I think this is somewhat more important than the thing we're actually talking about, and this is the idea you should really remember even outside of your class, outside of this class. And anyway, this is the backbone of all the Fourier transform we are doing. That we need to know. you need to have this idea that all those complex exponentials, they are functions that are orthogonal to each other. When you have different n, when you have different k, or when you have different r. When you have different k. They are orthogonal to each other in this inner product sense. So inner product for continuous time means you multiply them together and integration, and in discrete time means you multiply them together, then you sum over a period. And when your difference, when you have two different k, then they cancel out, because in continuous time you have this oscillation that will integration to 0, and in discrete time means that you have this point on a circle that will average back to the original point. Okay. So question about the orthogonality. If not, then okay, let's actually get back to the course material. So remember, we're talking about discrete time Fourier series. Okay, and so Fourier series, once again, we like our synthesis equation and analysis equation. And okay, so they are not as important as orthogonality, but they are still very important. So let's read through them. So synthesis relation equation, x of n equal to summation k equal in over n big N range, and ak times e to the jk omega naught n. And the analysis relation equation, a sub k equal to 1 over n, and summation and now it's summation over small n. So small n over a range, also over a range of big N, and xn times e to the minus jk omega naught small n. And and omega naught will equal to 2 pi over n. Yeah. And once again, this big N range means that we are summing over big N consecutive integers. So it can be small n from some n naught to n naught plus n big N minus 1. And a good choice of n naught is n naught equal to 0, then you are summing over k from 0 to n minus 1, or n from 0 to k minus 1. And now you see this is even more symmetric than the continuous time case, because you see this k and n, they are very similar. Actually, those two things are almost the same, except you have a minus sign here, you have a 1 over n here, right? If you just switch k and n. So this is some symmetry we'll talk about later. But yeah, so if you just write a instead of a sub k, you write a bracket k, then you can look x of n as some discrete periodic function with period big N, and ak also some periodic function with period big N. Okay. Yeah. And yeah, that's what we were thinking about. Although, okay, so this is a bit funny. So here, for the synthesis equation, we only need like a big N of ak. So we can just define ak, say we can just define ak from 0 to n minus 1, right? So ak can be just some function from 0 to n minus 1 and undefined or elsewhere. But it's more elegant and a lot, how should I say? Yeah, I guess it's more elegant and a lot easier on a lot of notation if we just extend ak as a periodic function, because this summation can be any interval, so we just define ak also as a periodic function with period big N. And that will make a lot of things a lot easier. Then we can have our summation of n to any interval. Yeah. So anyway, yeah. So we have ak equal to ak plus big N, and that means that if we think ak as a function of k, then it's periodic with period big N. And that's consistent with all the equation we write down. And also with the interpretation, so let's try to jump back. So the interpretation of ak is a coefficient for this function into a jk omega n, and we have to say that this function is the same function if you take k to k plus n, etc. But anyway, ak is now a periodic function with period big N, and those two equations is the discrete time Fourier transform. And another thing we have been saying is that there is no convergence issue for discrete time Fourier transform. So those two equations always exist for every possible xn and every possible ak. Every xn we're gonna find ak, and this convergence is perfect because you are solving n linear equations with n unknowns. Yeah. And yeah. Oh, here we have another name, so ak is called a spectral coefficient. Okay, question about our synthesis equation and the analysis relation equation? If not, okay, we have 15 minutes, and there should be plenty of time to go over the examples. So, example of discrete time Fourier series. And so, for example, it's very easy. Excuse me. So once again, we are breaking up the sine function. So we have sine omega naught n. Excuse me. And here we pick a very easy omega naught. So omega naught is 2 pi over big N. So remember that this grand case is also funny. So if omega naught is not some rational times 2 pi, then this is not even periodic. But here we pick a very good omega naught. Omega naught equal 2 pi over sine integer big N. So this is fundamental period big N. And then we can use our reverse Euler. Once again, we just break this sign equal into the linear combination of two complex exponential. So 1 over 2j is e to the j something minus e to the minus j something. And so we don't even need to do the summation here. We just break this into complex exponential directly, and we can read the coefficient here. So because those are already complex exponential, so you see that we have a1 is just this 1 over 2j, And then we have a of -1, because you have a minus sign here, so that's a of -1 will equal to -1/2j. Okay. And all other ak equal to 0. Okay. And so if we want to plot this, then we need to find the k. So let's say we pick we need to pick n. So if we pick n equal to 5, then we can plot this ak in a line. So it's ak as a function of k. And okay, so as we said, at k equal to 1, we have 1/2j. So we are plotting the okay, so this is a bit funny. But anyway, we're plotting the negative imaginary part of our AK. So 1/2j here and negative 1/2j here. And as we said, we pick n equal to 5, and AK should also be periodic with the same big N. So it should repeat every 5 points. So those -1 value should equal to this +4 value, and this 1 value should equal to this 6 value, and they keep repeating. So yeah, so you can pick the period you like. So maybe like from -3 to +2 is one period, and keep repeating, or you can pick from 0 to 4, and you'll keep repeating in this area. Okay, so this is the plot of AK. It's a function of k, and it's the same period as the period of your x of n. Okay. Question? No? Okay, then let's see a more complicated example. Now we have a whole bunch of signs, so sine and cosine. So 1 plus sine 2 pi over n small n, 3 cosine 2 pi over n small n, and then this cosine 4 pi over n plus pi over 2. But it's not very different from the previous example. You just break your sine and cosine into complex linear combination of complex exponentials. So once again, sine become 1/2j e to the j something minus e to the minus j something, and cosine equal to cosine equal to 1/2 e to the j something plus e to the minus j something, and this is cosine also similarly. And now we just collect the terms. Okay. And here, I guess the first thing we need to see is we need to determine the fundamental period. But fundamental period here is nice. So 1 has period anything. So this sine has fundamental period n, and this cosine has the same fundamental period big N. And now this cosine part is this 4 pi over n, and so this is a fundamental period big N over 4 if that's divisible. But anyway, it will also have fundamental period big N. It might be smaller, but big N is also one with fundamental period. So sorry, fundamental don't have one. Big N is also one with period. So you see that this whole thing has fundamental periods big N. Yeah. Okay, so fundamental period is nice here. And anyway, we break those into complex exponentials, and now we just collecting terms. So we have some HR pi over 2 here, and you just take it out as HR factor. You get some HR factor e to j pi over 2 here. And now you look at all those complex exponential and collecting a term that has same k. So you have e to the j 2 pi over n, e to the j 2 pi over n here. So you combine those two terms, 3/2 plus 1/2j, and similarly here 3/2 minus 1/2j, and those things they have different k, so they have this 4 pi n over n, that's 2 times 2 pi over n, so we have k equal to 2 here, that's nice. and it has extra phase with only is pi over 2 as we said. And anyway, so we see the fundamental period is this n, and the fundamental frequency is this 2 pi over n, and so this one will corresponding to the DC term as usual, so this is A naught. And for k equal to 1 is this term, so A1 equal to this thing. And A2, A minus 1 equal to this thing. And then you have A2 here, A minus 2 here. And if you have a larger n, then you have some other AK, but those are all 0. Okay. This is a pretty direct example. And yeah, we plot this on so we plot, okay, I guess, okay, let's do this. Okay, and we plot this, oh, can you still hear me? Hope so. So we plot this on this graph here, so once again we plot the A of k. And now those are complex values, so we plot the magnitude and angles. And okay, so what's the n here? We didn't quite say, but I think n is 5. N is like 10 here. Okay, so big N is about 10 here. And anyway, we plot the relevant AK in the middle cluster. So we have A0, A1, A plus minus 1, A plus minus 2 here. And they have some complex angles we also plot here. Okay. Question? Okay, if not, then let's see. I believe this is the next example. Okay. The next example of the discrete time Fourier series. So now we back to the square wave function. Now we see this is very different. Not very different, but kind of different from the continuous time. So we have our, well, I guess not quite square wave, but looks a lot like square wave for discrete time. So we have those functions that's 1 from minus n1 to n1, and it's periodic with period big N. Okay? And it's 0 otherwhere. So it looks very like a square wave, but now it's a discrete time function. And now this thing we don't have an easy way to break. It's not just sine and cosine, so we can break into complex exponential. So if we want this Fourier series coefficient, we need to do actual calculation with our analysis equation. And okay, so this is basically brute force calculation of AK. We plug in the formula 1 over summation from 1 period. And from 0 to n to 1, 1. Okay. So anyway, oh, we're doing something funny here. So we have plugging this thing and the summations on n and xn, which is just 1, and our exponential e to the minus jk 2 pi over n small n. And so this x over n does nothing but restrict your summation from minus n1 to n1. Okay? And here we already do some change of variable. So from minus n1 to, so we are summing over, we need to sum small n from minus n1 to plus n1. And it's a bit funny. But anyway, so instead of minus n1 to n1, we can sum from 0 to 2n1, and like doing a change of variable, so we change from n to, so we have n equal to m minus n1. Okay? So from n to m, and we get this extra n1 factor here because it doesn't depend on the summation m here. Now we are summing over some n from 0 to 2n1 e to the minus jk 2 pi over nm. So this is doing some change of variable from n to m. And this thing, now this is just a geometric series because, yeah, this is some m. And so this is e to the jk 2 pi over n to the mth power, right? So we are summing over this complex exponential with m here, and this is actually is complex exponential to the mth power. So this is a geometric series, and we can use a geometric series equation. And this is 1 minus a to the r plus 1, no, e to the minus a to the r. And r here is the number of term here is 0 to 2 and 1. So there are 2 and 1 plus 1 terms here. So this is geometric series equation. And this is kind of the answer, but we want to make it a nicer form. So we have 1 minus complex exponential, 1 minus complex exponential. So we try to make it into a nicer form by putting this into sign. So 1 minus complex exponential is a lot easy, not really easy to see, but if we have a complex exponential minus a complex exponential, then that's proportional to sign, right? So we take our factor of basically a square root 2 of this thing. Yeah. Okay. And so we take some factor on the upper side and some factor on the lower side. And so we have complex exponential minus complex exponential, complex exponential minus complex exponential. And then we keep track of all the extra factor, and they will actually all cancel out nicely. And anyway, so we end up with a sign here. So because this thing is sine something times 2j, and this is sine something times 2j, and the 2j cancel out. And we end up with this thing. So ak equal to 1/n, and sine something times k. Okay, so I should say a little more. So sine 2 pi k n1 plus 1/2/n, and over sine pi k over n. So some sine over sine. Okay, and here we have will sound like a sine k over sine k, but we have a n1 factor here. So that's very brute force calculation, but we can do some plotting here to give you some idea. So once again, we plot aka with respect to k, and this is all real because it's just sine over sine. So we just can plot the value. And here we are taking n1 equal to 2, and we are plotting this with different n. So n equal to 10, then we have this thing, and n equal to 20. You can see this k is all periodic. So when n equal to 10 is periodic with period 10, and n equal to 20 is periodic with period 20, and n equal to 40 is this thing. And you can see when n gets n get bigger, it's kind of getting back to what it looked like for the continuous sign case. For continuous sign case, we have those sine or sine k over k thing, and sine k over k will have this bigger peak in the middle and decaying out, etc. Anyway, here we see that the AK has the same period with your x of n, and when n gets bigger, this gets more spread out. And the most important thing is, no matter what your n is, when you add back your series, then you will get your square root perfectly. So remember, in continuous time, we have those weird Gibbs phenomena overshoot at the edge here. But for discrete time, there is no overshoot. You add back the series, you get back your series, you back your discrete time signal perfectly. There is no convergence issue and no Gibbs phenomena. Okay. Oh, exactly on time. Okay. So any question? Otherwise, today will be this, and we'll midterm next Friday, and some review next Tuesday. Okay? Okay. Then see you next week.